In this presentation, we're talking about input-output design concepts for a computing system. These are the basic ways that input-output for computing systems is implemented. And in this presentation, we're going to explain these design methods, the basic design methods, and illustrate with some examples how they can be implemented in hardware. To make sure that we have a common framework of reference, let's go over the very basics of a computing architecture. So we have here a CPU with various registers that I have discussed on a previous lecture. Then we have memory. Now this is shown as a single block, but it may be different memory banks or different memory hierarchies. And then you have peripherals. Over here you have the buses, the data bus and the address bus that facilitate the communication between the CPU and peripherals. And here, shown in blue, is the control bus, which is all the control signals that are exchanged between CPU and memory or peripherals. Out of all the signals, the most important one is probably the read-write signal, which determines whether an operation, an input-output operation, which the CPU has initiated, is a read or a write operation. There are other signals that are common and important, such as the interrupt signals and the interrupt acknowledgement signals. But for now, we're going to stick to just the read-write signal for this. Now let's turn specifically to the input-output issue and how the CPU talks to peripherals. One way that a peripheral is accessed is by placing its address, the one that is allocated with a particular peripheral, on the address bus, right here. The peripheral, its peripheral, by monitoring the address bus and recognizing that its address appears on the address bus, knows that the I/O operation is intended for it. For simple peripherals which do not do their own monitoring, a decoder does the monitoring and activates that specific peripheral after decoding the address that is on the address bus. Other peripherals may have their own decoder that is able to decode the address that's been placed on the address bus. The peripheral that has been activated either because it detected its address on the address bus or because it received a signal, an activating signal from the address decoder, is the one that will respond to the control bus signals, mainly the read and write signals, and either grab whatever data is on the data bus or drive data which it generates onto the data bus. Let's consider the case where the CPU is sending data to a peripheral, say for example a printer. Typically, the CPU will do the following. First, it will drive the data on the data bus. So the data bus here will contain now the data, or at least part of the data, that the CPU wants to communicate to the peripheral. Then it will drive the address of the peripheral on the address bus to indicate who it is trying to talk to. So once the CPU has driven the data that it wants to communicate on the data bus and the address of the peripheral on the address bus, then it issues a read-write signal. Now, obviously, only that peripheral, which is the intended destination, is going to grab the data from the data bus. Similarly, if the operation is an input operation, so the peripheral has to generate the data, say for example the peripheral is a CD drive, then The same cycle happens, except that the CPU does not drive any data on the data bus. It simply will provide the address to the address bus, and then it will issue a read signal, which the intended peripheral is supposed to interpret as a go to produce data and drop it on the data bus from where the CPU is going to pick it then. Let's look a little closer to how these operations and the CPU peripheral communication can happen. A decoder, this one, monitors the address bus and decodes the addresses that the bus is currently carrying. Then it activates the appropriate peripheral depending on what address it detects on the address bus. That peripheral then will be the one to respond to the control read-write signals that are issued by the CPU, either to get stuff from the data bus and do something with it, or to produce data and drop it on the data bus. That is determined by whether the control signal from the CPU is a read or a write signal. In an alternative arrangement, peripherals may be more sophisticated and have their own decoder, which allows them to decode directly an address that is on the data bus and identify whether the CPU is trying to talk to them or not. A peripheral may also have more than one addresses associated with it. This is because it may be able to perform a variety of functions on the data, and the specific address by which it is activated indicates which function exactly it is supposed to perform. Now let's go back to the example where the CPU intends to send data to the printer peripheral. This printer has some mechanical parts which transport paper, move print heads, etc. So it takes time to process a print request, and until the current print job is done, it cannot process another. At the same time, the CPU cannot send all the print data in one shot because the data bus width is limited. So it has to break up the data in blocks which can individually fit on the data bus and send them in a sequence. The peripheral typically has a buffer to hold the next jobs, but that too is finite and can get full, thereby not being able to store any new data communicated from the CPU. So a printer, for example, does have a buffer that buffers the data that the printer is sending, but if the print job is too big, there's too many pages with graphics and what have you, that can overwhelm the buffer. So it is necessary to have a scheme where the CPU can recognize that the peripheral cannot handle any more data and hold off and wait before it sends any more data. So before the CPU can send or read any data to or from the peripheral, it first must ensure that the peripheral is ready or available or functional. Hence, there is a need for the peripheral to produce status information on some status signals which the CPU can read in order to determine its status. Thus, every access to a peripheral must be preceded by a poll of the peripheral to determine that it is in fact ready. This is the polling method, which is actually a protocol for performing input-output operations. So this is the polling method, and here is a summary example for how the CPU can access a peripheral with this polling method. First, the CPU will perform an I/O read operation to read the status of the specific peripheral. So the peripheral will be able to drop its data on the data bus from where the CPU can read it. So getting this status information requires a read cycle by the CPU. Over here in this example, we have a tri-state that tri-states the status signal or signals that are generated by this peripheral. It may be just one signal indicating whether the peripheral is ready or busy, or it may be more than one signal indicating a variety of different states in which the peripheral may be. The tri-state is a very specific electronic piece, a very simple one too, which does a very simple job. When activated with a control signal, it will allow its input lines to connect to the output lines and transport their data from one side of it to the other. But if it is not activated, then the output side is floating, which means that it is disconnected from the input side. Now that is not the same as with a register, where the output may be either zeros or ones. When the tri-state is not activated, its outputs are not zeros. They're not grounded. They are floating. So they are like you have cut them with scissors, and they are wires that are floating. So in this example, we assume that this tri-state has an address, I/O address, that is allocated to it. So it is, for all practical purposes, some kind of external device that the CPU can actually read. So the CPU places the address for this tri-state with the status information on the address bus. The address decoder decodes that address and activates the tri-state. Therefore, the tri-state carries the status signals onto the data bus. Then the CPU can read this information. With the status info, the CPU determines whether it is okay to send or get data to or from the peripheral. If it is okay, i.e. the peripheral is not busy and it can perform the operation, the I/O operation, then the CPU places the address of the peripheral now on the address bus, the one that will activate the peripheral to produce its data or to get the data from the bus. The address decoder will activate the tri-state to connect now the output of the peripheral to the data bus, and at the same time it will activate or enable the peripheral, thereby giving it a go signal to do the job that it is supposed to do. Then the peripheral will produce its data, which through the output lines and the now activated tri-state on this side will drop the data on the data bus from where the CPU can get the data. Now, if the status information that was read earlier indicates that the peripheral is not ready, then the CPU will simply keep polling it and reading the status information of it until it has found it clear to proceed and therefore proceed with the job. So we have a loop over here where the CPU keeps reading the status information and waits until the peripheral is found not busy or ready to perform the job and therefore proceed to perform the job. Another note over here, there are different tri-states on these lines because you can only have one line driving a corresponding one on the data bus. Okay, you cannot have more than one lines actually driving the same line on the data bus, because if they're not in agreement, one is trying to drive a 0, the other is trying to drive a 1, then the results can be unpredictable, let alone dangerous, because if one line is driving a 0, the other line is driving a 1, then that means that one line is trying to ground the corresponding bus line and another one is trying to inject power to it, and therefore you have a situation where power might get straight to the ground. That's why normally you have tri-states like these and control signals, activate them to make sure that only the appropriate ones are passing on signals at any given time. And that, in short, is the polling method, which is not very efficient. The method is simple, but it wastes a lot of the CPU's capabilities. A CPU, especially a very capable one, is an expensive piece of hardware, and a very sophisticated one too. And it is at least pity to have it simply wait around polling a very slow peripheral, which may be electromechanical and therefore very slow, such as, for example, say a plotting device that plots architectural designs on large format posters or paper. So you have electromechanical parts in this, and it takes time to move them around, and therefore its operation is very slow. And the CPU would be waiting around for a peripheral that is very slow, and that just doesn't make too much sense. Also, there has to be a delay between polling cycles. If the delay is very short, then the CPU spends a lot more polling cycles, which are practically wasted. If the delay is long, then the CPU will not be able to take advantage of all the availability of the peripheral. For example, say that the delay is 10 seconds, an imaginary number here, and the peripheral becomes available just 2 seconds after the last time it was polled. Then the CPU will not know until at least another 8 seconds, which is on the next poll, that the peripheral is in fact available. So those 8 seconds would be unnecessary dead time. So those are the problems with the polling method. And then we're wondering what would be a better way? To provide a way for the peripheral to immediately notify the CPU when it is available or when it needs attention. Hence, the interrupt method. With the interrupt method, a peripheral notifies the CPU that it needs attention, like more data to be transferred or a prior job has finished, etc. And therefore it needs either more data or further attention. Shown over here is the way that peripherals can request the attention of the CPU, which at the time may be doing something else. Now the CPU is supposed to at some point suspend or interrupt its current operation and turn to servicing the peripheral that requested its attention. This figure shows a simple implementation of the method. The CPU has one interrupt line. In reality, it may have more than one interrupt lines, some of which may be maskable and some of which may be non-maskable. Interrupt lines from multiple peripherals are ORed together, like this, in order to notify the CPU that some peripheral or peripherals need servicing. In response, the CPU accesses a port, which is shown over here as a simple tri-state to read the requests and determine which peripheral needs servicing, and then it proceeds to service it. It should be obvious that as a response to the interrupt, the CPU would put on the address bus the address associated with this tri-state that will activate the tri-state to pass the signals through onto the data bus from where the CPU will read them in order to determine which one of the peripheral or peripherals is requesting service. It is also important to note that while over here we're showing only one interrupt input for simplicity, there may be more, like I mentioned earlier. Some of these interrupts are called maskable because they can be disabled, they can be masked, or the CPU can deactivate them or activate them, or as we say, mask them or not. And some of them are non-maskable. Normally, non-maskable interrupts are reserved for high priority devices, which produce signals that are critical and they should not be masked off. Say, for example, you have a power plant and something happens that could lead to catastrophic consequences. The CPU has to attend to any sensor that is signaling that this part needs servicing. It cannot be left to wait. So you do have both of these kinds, but this is not critical for what we're describing now. So one interrupt line suffices for what we are trying to describe. So in more detail, one or more peripherals raise an interrupt signal to request servicing, i.e. the attention of the CPU. A single signal is produced by combining the individual peripheral interrupts and is fed to the CPU to request attention. At that time, the CPU may be processing another job, but it will interrupt that job and will jump to a routine, a special program area that is called the general purpose interrupt service routine. The purpose of this routine is to perform an I/O operation and identify which peripheral to service. It does this by reading, analyzing, and prioritizing the individual interrupt requests, which it can read from this tri-state over here. In this example, an I/O address is allocated to the tri-state buffer so that when activated by the address decoder, the individual interrupt signals will be driven onto the data bus from where the CPU can obtain them for further analysis to determine which peripheral to service. Typically, the general purpose service routine does the following sequence of steps. First, it should disable further interrupts, at least those which are maskable. It should perform a read I/O operation to get the individual interrupt signals. For this example, this general purpose service routine drives the address of the tri-state onto the address bus to activate it and then be able to read all these individual signals. Then this general purpose service routine determines which of the signals are in fact active, which ones are zeros and which ones are ones. If there is more than one signal that is active, which means that there are more than one peripherals requesting service, then it will have to prioritize. This priority is determined according to a priority scheme which the system programmers have programmed into the system. The general service routine passes the control to a special service routine which is specific for the service of the identified peripheral. This is done with a jump, and if you have seen my previous presentation, the jump describes how the very simple computer will store the contents of the program counter so that it can return. So everything that we talked about jumps in that lecture is useful here. Once the specific service routine for that peripheral finishes its job and the peripheral has been serviced, the program control returns, as discussed again in returning from jumps. Upon return, the interrupts are enabled if they were disabled, and the interrupted job is restored. Obviously, if there are any other peripherals that have issued an interrupt and they are waiting, once the interrupts are enabled again, the CPU will see another interrupt and it will then proceed to execute the general purpose interrupt service routine again, which will identify the next peripheral that should be serviced and then proceed with a specific service routine for that peripheral and then return, and the cycle can continue for as long as there are peripherals that have requested interrupts. And when all the interrupts are cleared, the CPU will simply return to restore the job that it interrupted in the first place. In another variation of the interrupt IO method, a priority encoder may be used to prioritize the peripherals and produce a code as output which identifies the peripheral to be serviced. That code is then driven onto the data bus to pass it on to the interrupt service routine. So rather than the interrupt service routine trying to determine which peripheral it should give priority to, it is the priority encoder that receives all the individual interrupt requests that determines which of the peripherals has the priority and produces a code, an identifying code for the general purpose interrupt service routine to know which peripheral needs servicing and therefore pass the control quicker to the specific service routine for that peripheral. So the priority encoder is a very simple combinational logic hardware that simply prioritizes the lines that may be active at its input and produces a code at the output when it is enabled, of course, to indicate which one of the input lines among those which are active has the priority. It does this in hardware and therefore it is very fast because the interrupt service routine does not have to perform the prioritization task. But the problem is exactly that it is hardwired and thus it is not easy to alter. It is easy to alter the priority scheme if it is programmed and the interrupt service routine is the one that is running that program to determine what the priority is. By changing the program, you can change the prioritization scheme. In hardware, when you do it in hardware, the priority encoder, it is much faster, but it is not flexible. It cannot be changed. You would have to go and change this piece of hardware. In summary, the basic tasks performed with an interrupt IO method are as follows. When an interrupt is received at the CPU finishes the instruction which is currently in the process of being executed. Typically, the CPU checks its interrupt inputs right before proceeding to the next instruction fetch. Upon receiving an interrupt, the CPU executes a jump to the general purpose service routine, and per the jump, it will save the program counter contents on the link registers so as to return and resume later. The general purpose service routine performs an IO read operation to get the interrupt identifier from the data bus. This may be the raw vector of signals, or it may be the output of a priority encoder. The general service routine determines which peripheral must be serviced and executes a jump to a special purpose interrupt service routine, which is specific to servicing that particular peripheral. When the servicing of the peripheral is finished, the previous jumps return, the interrupt inputs of the CPU are enabled if they were disabled, and the interrupted task is restored. Now we turn to another method, which is known as the Direct Memory Access method, or DMA for short. The Direct Memory Access method creates a temporary direct channel for data transfer between a peripheral and a memory bank. This is to facilitate cases where a large amount of data is to be transferred from a peripheral to memory or from memory to a peripheral. Typically, in such situations, the CPU is acting as the intermediary. It reads data from the peripheral and holds it temporarily in its accumulator, and then it performs a write operation to memory by passing its accumulator through the data bus to memory to write the data. Or, if it's the other way around, it will read data from the memory bank into its accumulator and then pass it on to the peripheral. So the CPU acts as an intermediary buffer, but otherwise does not do anything very useful. It is simply wasting its time just reading stuff from memory or peripheral and then passing it back straight away. With the DMA method, this intermediary job is outsourced to a DMA controller, and the CPU can be free to proceed and perform other tasks. So how does the DMA method work? First, the CPU performs I/O cycles to pass information about the transfer to the DMA controller. Typically, this information will consist of the following. First, it needs to tell the DMA controller what is the size of the block of data to be transferred. Then, it also must specify the starting address in memory where the block will be moved to or from. And also it has to specify the ID of the peripheral, which one is the peripheral that is involved in the transfer. This is typically the at minimum required information to specify the transfer. Then the DMA controller will carry out the transfer. It will be the one that will be providing the signals that otherwise the CPU would be providing, therefore freeing the CPU to turn to other tasks. Now, in order for the DMA controller to play the role of the CPU, it has to become the bus master and thereby simulate what the CPU was doing. Once it becomes the bus master, then it can replicate the actions of the CPU by issuing the exact same signals which otherwise the CPU would generate in order to carry out the transfer. In this example, after the DMA controller receives a go from the CPU, that is, once it's issued an IO to an address that it understands and which is to be interpreted as a okay, now go do what I told you to do, then once it receives the go from the CPU, it tri-states a section of the buses and becomes the bus master for these sections. What is shown over here is tri-states that are controlled by the same signal issued by the DMA controller. And of course, these tri-states can be controlled to float these parts of the buses, thereby the signals on one side are not connected to the signals on the other side. And so in this way you can float these parts of the buses. Then the DMA controller can become the bus master for these sections and replicate the performance of the CPU and facilitate the transfer from the peripheral to memory or memory to the peripheral. At the same time, the other sections of the buses where the CPU is connected can operate independently and the CPU can go on and perform other tasks rather than sitting there idle. However, it is not always possible to split buses and use memory bank modules in this way. See, in this embodiment, we assume that there is a memory bank over here that is accessible on this side of the buses and that the CPU does have access to a main memory or other memory modules so that it can continue fetching instructions and continuing execution of other programs instead of sitting idle. But like I said, it's not always possible to split buses and use memory bank modules in this way. Since the CPU needs to fetch instructions and data from memory, unless it's possible to do this trick, the CPU has to be able to use them, otherwise it will just sit over there idling and there would be no benefit to all of this. So unless you can do this trick, the DMA controller has to be able to access the memory in between the times that the CPU is trying to access it. Therefore, the DMA controller would be stealing cycles, memory cycles, from the CPU. This is what is referred to as cycle stealing with respect to the DMA method. When the DMA transfer ends, the DMA controller releases the buses. For this example, it deactivates the tri-states and it returns the control to the CPU. The example over here also shows the DMA notifying the CPU about the transfer completion via an interrupt. When the interrupt is received, the CPU would then turn its attention to the DMA controller and probably issue more transfer requests if any are pending. The benefit of the DMA method is that while the DMA controller performs the mundane tasks to transfer the whole block of data, the CPU can do other things in the meanwhile, instead of just sitting over there and using all its awesome capability to simply read bytes of data from one place and send them to another. Now, the DMA method refers to transfers between memory and peripherals. but there is no reason why this cannot be used to perform transfers from one peripheral to another. So the same method can be used to transfer data from, say, a CD, take a file from a CD or a flash drive and send it to a printer. The CD drive or the flash drive are peripherals, and so is a printer. So when this method is used for communication between peripherals, we refer to it as direct data transfer, or DDT for short. In this case, it is easier to isolate parts of the buses, as in the previous example of the DMA, and the CPU then can go on performing other tasks with unobstructed access to memory, free of the mundane I/O tasks for getting and moving data itself, which is now outsourced to the DDT controller. The channel I/O method. In an evolution of the DMA and the direct data transfer methods, the transfer controller is a more sophisticated component which can perform more than just transfers. For example, it may be a cheaper, less powerful CPU which can also execute simple algorithms, that is, program code. This allows the controller to be more intelligent and handle more complex I/O, much like the central CPU can, so as to be able to handle an I/O channel and free the central CPU from even more of the I/O burdens and the servicing of slow peripheral components. A channel can include many peripherals, and the I/O controller handles the I/O for those particular peripherals. There may be many channels, each with its own controller supervisor, such as shown over here. 3 different channels, each with its own I/O channel controller. The bus system then can be arranged so that the CPU can access the memory while the controllers of the I/O channels can transfer data in a separate I/O bus. In this example, there is a memory bus and an I/O bus which serve to isolate as much as possible the operations of the CPU and the I/O controllers. The 2 buses are bridged so as to make communication between CPU and I/O controllers possible, but also to make the CPU more independent from I/O tasks. In the case of DMA or that of DDT, the CPU had to initiate the transfer of data blocks by sending the transfer information, that is, what the source is, what the destination is, the starting location, and the block size. It had to send all this information to the controller. Likewise, in the channel I/O method, the CPU communicates needed I/O information to the channel controllers, but this information is more sophisticated and may include pointers to code or drivers to be used. A channel I/O controller can do more things than its simpler predecessor DMA or DDT controllers could do. It may, for example, translate addresses or perform more sophisticated controls on the peripherals based on programming that the CPU makes available to it and which may handle resolution of problems during I/O. In the case of DMA or DDT, problems with I/O are passed back to the CPU for resolution. The CPU is the one that has to decide and handle problems, if any, appear. However, with the channel I/O method, the individual channel controllers are smarter and more capable and can resolve problems as well. They can do that under the control of code, programming that is passed on to them by the CPU. The issue with memory cycle stealing from the CPU is still present. It's just that it is not as much pronounced. Often, the channel controllers may need to access memory either because they need programming to access programming in order to know what to do with certain peripherals or certain situations, but that communication is not as often because that communication can be kept to a minimum. Nevertheless, cycle stealing from the CPU is still present. In this last part regarding I/O, we turn to another concept known as daisy chaining. According to this concept, peripherals are cascaded on a chain. They submit service requests to the CPU as needed. Typically, in this scheme, the peripherals may have controllers which can carry out the needed service, so in reality, the request is for granting control of the buses so that the peripheral controller can carry out the operations, such as be able to access the buses or other resources as needed. Simultaneous requests must be prioritized, and the priority is resolved by the physical position on the daisy chain. Typically, daisy chains work as follows. Upon receiving a request, shown over here in this example as an interrupt, that is produced once one or more peripherals request service, the CPU sends an acknowledgement to the peripherals. The first one on the chain gets that signal. If it has an active request, then it blocks it from further propagation, and then it becomes the bus master, completes what it needs done, and turns off its request. If this peripheral does not have an active request, then it simply allows the signal to propagate to the next one. So the CPU responds to an existing interrupt, therefore there has to be some peripheral that is expecting service or more. And by this scheme, the peripherals are going to be checked one by one, starting with the very first one on the chain, to see which one asked for the service, and then that one is going to be the one that gets serviced, which in reality means that it interprets the interrupt acknowledgement as a signal to go ahead and take control of the buses in order to do what it needs to do. The priority scheme with this method is hardwired and fixed by the physical order of the devices on the chain. Devices closer to the CPU will be greedy, and those that are farther will be more starved of access privileges because they have to yield to the ones ahead. These are the basic methods that are known in computer architecture as the basic I/O methods. Thank you for staying with me.